Hello, everyone. So this is lecture 5. In this lecture, we're going to talk about the properties of matrix operations. So the learning objective is that we want to be able to recognize properties of matrix additions in scalar multiplications and familiarize ourselves with the properties of matrix multiplications, including powers of matrices. All right. And at the end, we try to familiarize ourselves with the properties of the transpose of the matrix. And what is the transpose of the matrix? We're going to find out later in the lecture notes. All right, so the first part of the lecture is to focus on the properties of addition in scalar multiplications. There are multiple properties that you may want to know. So the setup is that you have three matrices A, B, and C with the same sign, and two scalars or constant R and S. So these are real constants. Okay. So the first property is that we already see this property in the last lecture that the product, the sum is commutative, or that A plus B is equal to B plus A. This property has the name is called commutative by addition. The second property is the associative property, that if you do A plus B and then add another matrix C, is going to be equivalent to doing the addition of B plus C first and then add with A later. So this is the associative property. The third property is additions of the zero matrix, right? So if you have a zero matrix of the same size as A, then A plus zero matrix is equal to the matrix A itself. Number 4 is the additions of the opposite side of A. So A plus negative A is going to be equal to the zero matrix. So let me quickly note that zero, in this case, the zero matrix of the same size as A. Okay. All right, so the next property is scalar distributions. So if you have R times A plus B, it can be equal to or is equivalent to A R times A plus R times B, right? If you do the matrix addition first and then scale it, it's equivalent to doing the scale of each matrix and then add them together. So this is distributive property. There's another distributive property for scalar multiplications, that if you have two different scale, you can add the scale together first and then multiply with the matrix A, or you can scale the matrix A in two different manner and then add them together. Right, so this is also distributive. And the last property is associative by scalar multiplications. That is, you scale the matrix A by S first and then scale that with R, is equivalent to doing the product of R times S and then use that to scale the matrix A. Or you can just scale the matrix A by R first and then scale that with S. So it's going to be the same thing. So these are the properties of matrix additions and scalar multiplications, right? Moving on to the next set of properties, the properties of matrix multiplication, which is a little bit more complicated because it's not as straightforward as you may think when you do matrix multiplications. Because if you do matrix multiplication from the left, is going to be different from doing the matrix multiplication from the right. And you will find out in a minute here. All right, so let's consider the following matrix, following matrices A, B, and C of which or whose sides are such that the indicated operations can be performed, right? So that means, remember, for the matrix multiplications, the side of or the dimensions of the column of A has to be the same with the dimensions of the row of B if you want to do A times B, right? So you have to be careful on the side of the matrices you want to perform the matrix multiplications on. Right, in this case, you also have a scalar, and I call that scalar K. All right, so the first property is the associative property. So if you do A times B times C, it's going to be equivalent to doing A times B first and then times C. Right? You can see the order on which I write the matrices has to be very distinctive. That it has to be in this particular order, right? If you want to do A times B times C, this is also A times B times C. So this is associative properties. Right, the next property is called the left distributions. If you have A times B plus C, because the multiplication or matrix multiplication happened on the left hand side of B plus C. So therefore, when you do the distributions, the matrix A has to be also on the left of matrix B and on the left of matrix C. Right, so the distribution is A times B plus A times C. This is called the left distributions. Right, and this is quite important because you also have something called the right distributions. And because, so B plus C times A, because now A is on the right of the sum B plus C. So therefore, when you do the distributions, A has to be on the right of B and A is on the right of C. Right? So you get B times A plus C times A. Right? This is the right distributions. Okay. The next one is the associated by a scalar multiplications. That is, if you have a product A times B, you can perform the product and then scale using the scalar K. Or you can scale the matrix A first and then multiply with the matrix B. Or you can scale the matrix B first and then multiply with the matrix A. All right. The next property is the identity for multiplications. You have the identity matrix of the side M multiplied with A. It's going to be equal to A, or is going to be equal to A times I N. Right? So this is the identity matrix of M by M. This is the identity matrix of N by N. And so this is the property of identity for matrix multiplications. And we have this different set or different type of identities because if we have a matrix A of the form or of the side M by N matrix, right? So you have to be careful here. Okay. Okay, so that is, these are the properties of matrix multiplications, right? The associative properties, two very important distributions properties, that is the left distribution and the right distribution. So the order on which you write the products really matter because most of the time, for the most part, the product AB is going to be different from the product BA. Right? So that's why you have left distribution and right distributions. So this is the warning I want to give that most of the time, for the most part, A times B is not commutative. Okay, so AB is different from BA, right? So we also see this in the last lecture as well. So AB equal to BA is not always true. Okay. And because of that, something called the cancellations laws does not hold, right? Do not hold in this manner. That usually you have, for example, AB equal to BC, and you can do the cancellations on both sides. You get A equal to C. That's for the regular math that we do. But for linear algebra, that particular cancellation, the law does not hold. Okay, so that is even if AB equal to BC, sorry, AC, right? Then B and C may not be the same. Okay. So the last warning is that it is possible for the product to be equal to 0 or the 0 matrix, even if A is different from 0 and B is different from 0, right? In other words, the matrices A and B cannot, like sometimes are not 0 matrices, but the product can give you a 0 matrix. Okay, so you have to be careful with this 3 warning. The first one is that matrix multiplication is not always commutative. That's why we have left distributions and right distributions. The cancellation laws do not hold for matrices or for the product of matrix. Even if you have AB equal to AC, then B and C may not be the same. And you can have a product to be equal to 0, even if the individual matrices are not 0 matrices. Okay. The next set of properties is the powers of matrices. Now, if you have a square matrix, n by n square matrix, and there are 2 non-negative integer, so that means R and S are 0, 1, 2, 3, 4, 5, so on and so forth, or -1, -2, -3, so something like that, right? So they are integer. They increases by 1 at a time. You have A to the power R is going to be equal to A times A times A, right? So you do this R times, right? To get the power A to the power R. Right? If you have A to the power R times A to the power S, it's going to give you A raised to the power R plus S. Okay, so very similar to laws of exponents that we have learned in pre-calculus or college algebra for that matter. Number 3 is that A to the power R raised to the power S is equal to A raised to the power R times S. Right? Again, this is very similar to the case of law of exponent. All right, so those are the properties that you want to look at, right? In the next example, I want to revisit the idea of a product of 2 matrices, right? Because it's important for you to know that the product is not always commutative, right? So that is A times B is not always going to equal to B times A. So consider the 2 matrices of the form, right? So 2, 4, -1, -2, and 1, 0, 1, 1. So these are the 2 by 2 matrices. So the product is going to be 2, 4, -1, -2 times 1, 0, 1, 1. Right, so this give me the answer is going to be 6, 4, -3, -2. Right, so hopefully at this point you are familiar with the matrix multiplication. So I'm going to skip on the formality and just give you the answer. Now for the product B times A, the setup is 1, 0, 1, 1. and you multiply with 2, 4, -1, -2, and the product, this particular product, give you 2, 4, 1, 2. And you can see that A times B is totally different from B times A. So this shows that A times B is different from B times A for the most part, right? Again, there are some cases that allow you to see that A times B equal to B times A, but in general, again, the product is not commutative. Okay, moving on to the next example, which is to calculate the power of the matrix. Given this 2 by 2 matrix and you want to raise that to the third power, what you do is you can rewrite this as 1, 0, 3, 2 times 1, 0, 3, 2, and do another multiplications of 1, 0, 3, 2, right? So there are three, you have 3 matrices multiplied together, so three times, right? What you can do is you can either start by multiply these 2 matrices together, or you can do, sorry, and then after doing these 2 multiplications together, you can, the resulting matrix multiply with the remaining matrix right here, okay? Or you can just do this product of the these two matrices, and then the resulting matrix you multiply with the remaining one. Okay, so either way should work. So what I do is I'm going to do these 2 matrices multiplied together. So I get, right, the product's going to be 1, 0, 9, 4. And then I'm going to multiply with the remaining matrix 1, 0, 3, 2. And the result is 1, 0, 21, 8. Okay, so you have a power, you raise that, you have a matrix, you raise that to a certain power, you just basically list all the how many times you get, right? So in this case, you have 3 times, right? You list them out, do the multiplications multiple times to get the answer. Eventually, toward the end of the semester, there's a technique called the diagonalizations, which is extremely useful for us to actually doing the matrix power of a matrix. When you have a complicated matrix and raised to a very high power, okay? But that's for a much later part. But for now, this is how you perform the calculations on the power of a matrix. Okay. The next definitions or the next type of matrix I want to focus on is called the transpose of a matrix. So what is the transpose of a matrix? So the transpose of an n by n matrix A is an m by n matrix A is the n by m matrix and is denoted as A with the capital T on top of that, right? So the transpose of the matrix A has the sign that where you switch between the row and columns, right? So the rows become the column and the column becomes the row. Okay, so so this transpose of a matrix can be obtained by interchanging rows and columns of the matrix A, right? So that is the I row of A becomes the I column of A transpose. All right, so for all value of I, right? So depends on how many rows of I you can do on the performance to change that to the columns of A transpose. All right, so let's do a quick example on how to obtain the transpose of a matrix. So this is the column matrix of the sides 2 by 1. So you have 2 rows and 1 column. A transpose give you 2A. So this is the row matrix of the side 1 by 2. Okay. Now this is the row matrix of the side 1 by 3 because you have 1 rows and 3 columns. And the transpose of that is 5, -1, 2. All right. And so this is the side of 3 by 1. This is the side of 2 by 2 matrix, but the transpose becomes A, B, C, D. Right? So the rows become columns, rows become column. Okay. This is also a 2 by 2 matrix. The next matrix is the 2 by 3 matrix. So the transpose is going to be a 3 by 2 matrix. Right? Again, rows become columns, columns become rows. So D transpose is going to be equal to 1, 3, 2. And this is 5, 0, 1. And this is 3 by 2 matrix. For this matrix, this is a 3 by 3 matrix. And the transpose is going to be, my rows becomes columns. So 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth, right? So again, the transpose of the matrix can be obtained by interchanging rows in columns of the matrix A, right? So rows become columns, columns become rows. So the next set of properties I want to focus on is the properties of the transpose. So if you have 2 matrices A and B, whose size are such that the indicated operations can be performed, and let K be a scalar. Right? So a transpose of a transpose give you the original matrix. The transpose of the sum is the sum of the transpose. The transpose of a scalar multiplications or the scalar multiple of a matrix A is equal to K times A transpose. What it say is that you scale the matrix A and find the transpose, or you can just do the transpose first and then scale the resulting matrix later. Okay. The next one is the transpose of the product is equal to B transpose times A transpose. So it's a little bit different than you may think, right? So here the transpose of the sum is the sum of the transpose, but the transpose of the product is equal to B transpose times A transpose. The transpose of a matrix power is that of the matrix transpose raised to that particular power for all non-negative integer k. Okay, so it say that you can raise the matrix A to a certain power and find and take the transpose, or you can take the transpose of the original matrix and then later raise that to the k power. All right, so let's do some calculations here, right? Given two matrices, right, A and B. So matrix A is of the form 3 by 3, right? And B is the matrix of the form 3 by 2, right? So I want to perform A times B and raise that and take the transpose And then later on, I'm going to do the product of B transpose in A transpose, just so that we can compare the fourth properties of transpose. Right, so A times B give you 2, 1, negative 2, negative 1, 0, 3, 0, negative 2, 1. You multiply with matrix B, 3, 1, 2, negative 1, 3, 0. So the result of this product is of the form 2, 1, 6, negative 1, negative 1, 2. Now you're going to find the transpose of A times B. That means you want to take the transpose of this matrix. Right, so this give me 2, 1, so rows become columns, column become rows, right? So this is a 3 by 2 matrix, and the resulting transpose is going to be a 2 by 3 matrix. So 2, 1, 6, negative 1, and negative 1, 2. All right, so that's A times B transpose. Now you want to do B transpose times A transpose. So that means B transpose is 3, 1, 2, negative 1, 3, 0 transpose. And this is 2, 1, negative 2, negative 1, 0, 3, 0, negative 2, 1 transpose. So the transpose of matrix B give you 3, 1, 2, negative 1, 3, 0. And we're going to multiply with 2, 1, negative 2, negative 1, 0, 3, and 0, negative 2, 1. And so you're going to perform matrix multiplications for these two matrices. And we're going to get the resultant matrix of the form 2, 6, negative 1, 1, negative 1, 2. So through this example, through these calculations, we just show that AB transpose is equal to B transpose times A transpose, right? So this shows that, implies that AB transpose is equal to B transpose times A transpose. Okay. Now, moving on to the next definition is symmetry of matrix. So a matrix, so a square matrix A is symmetry if A, the given matrix, is equal to its transpose. So that is, so a square matrix. So it has to be a square matrix. Okay. A is symmetry if A transpose is equal to A. Right. That is, A is equal to its own transpose. Okay. So in the next example, we're gonna write down the transpose of matrix A and matrix B and see if the transpose is equal to the given matrices or not. So you can see that A transpose, right? So columns, rows become columns, column become rows. So A transpose is going to be the same, right, as A. Therefore, you say that A is a symmetry matrix. Sorry, symmetric matrix. Similarly, for the case of B transpose, it's give me 1, 2, negative 1, 3. And as you can see, this is different from B. So you conclude that B is not a symmetric matrix. Okay. Next example, I'm going to do a series of calculations on matrix A and matrix B to find the transpose and to see if the calculated matrix, if the calculated matrices are symmetric matrix or not. Okay, so for A, right, so you get A transpose equal to 1, 2, 3, 4. Right. So of course, A is not a symmetric matrix. So A's transpose is different from A. So A is not a symmetric matrix. Okay. And let's do A plus A transpose. So A is 1, 2, 3, 4. And A transpose is 1, 3, 2, 4. Add these two matrices together, you get 2, 5, 5, 8. And if you do A plus A transpose, take the transpose of that sum, it will give you 2, 5, 5, 8 again. Right, so let me do a little bit more formal. So take the transpose of this matrix, of course, you get the same thing, right? And this is equal to A plus A transpose. So therefore, you conclude that A plus A transpose is a symmetric matrix. Okay. Why do we do this type of calculations? Later on, we're going to draw conclusions, or when later on, when we're going to generalize the idea of this given matrix added with the transpose of this matrix to see what happened. Okay. The next calculation, the next part is to calculate the transpose of B, the product of B times B transpose, and the product of B transpose B. Right? And we also want to see if you have a symmetric matrix from this calculations or not. All right, so the B matrix B transpose is that of 4, -1, 0, 2, 3, 1. You take the transpose of this and you get 4, -1, 0, 2, 3, 1. And of course, this is different from the matrix B. So you say that B is not a symmetric matrix. Right. So given this matrix B, you say that B transpose is different from B. So B is not a symmetric matrix. The next calculation is to do B times B transpose. So you get 4, -1, 0, 2, 3, 1. And you multiply with 4, -1, 0, 2, 3, 1. And this is a 2 by 3 matrix. And this is a 3 by 2 matrix. So the result has to be a 2 by 2 matrix. And you do the calculations correctly, you will obtain the matrix of the form 17, 5, 5, 14. Okay. And if you take the transpose of this, you get 17, 5, 5, 14 transpose, or it's going to be the same as B times B transpose. Okay. And therefore, you conclude that B times B transpose is a symmetric matrix. Okay. The next calculation is B transpose times B. So B transpose is 4, -1, 0, then 2, 3, 1. You multiply with 4, -1, 0, 2, 3, 1. Right. Again, this matrix is a 3 by 2 matrix, and this matrix is a 2 by 3. So therefore, the resulting matrix has to be a 3 by 3 matrix. And the result is, so if you do the calculations correctly, you will get the matrix of the form 20, 2, 2, 2, 10, 3, 2, 3, 1. All right. And if you take the transpose of that matrix, of this matrix right here, you will get the same matrix, so 20, 2, 2, 2, 10, 3, 2, 3, 1. Right. So this is equivalent to B transpose times B. And therefore, you conclude that B transpose times B is a symmetric matrix. Okay. So this led us to a theorem to generalize the two cases that we have in the last example, that if A is a square matrix, if A is a square matrix, then A plus A transpose is a symmetric matrix. Okay, and we show, we're going to prove these two statements, but we have one example in we have the calculation from the previous example to show for this statement. And the second statement is for any matrix A or B for that matter. It's just a letter, right? So you can substitute that for all the letter. For any matrix A times A transpose and A transpose times A are symmetric matrices. All right, so let's prove this two statement, because it's a very straightforward proof, and we're just going to use the properties of the transpose of the matrix to show for this two statement. All right, so for the first statement, we want to show that A plus A transpose is a symmetric matrix. Given that A is a square matrix. So this is for the first statement. Right. So now we have the assumption that A is a square matrix. So we're gonna take the transpose of A plus A transpose, right? And this give you A transpose. So the transpose of the sum is the sum of transposes, right? Plus A transpose. And this is the second properties from the set of properties of transpose. So property number 2. Right, so that allows us to write that the sum of transpose is, the transpose of the sum is the sum of transposes. And the transpose of A transpose will give you the original matrix. So this is property 1. This give you A transpose plus A, right? Or we just rearrange the terms here, A plus A transpose. Then by definitions of symmetric matrix, this show that A plus A transpose is a symmetric matrix. So by the definitions of a symmetric matrix, or of symmetric matrix, A plus A transpose is symmetry, okay, or a symmetric matrix. Okay, so that's the first statement. Now for the second statement, we don't have to have any specific dimensions for A, right? So in this second statement, the matrix A is of any size, right? So for any matrix A, right, we get that we're gonna take the transpose of the product AA transpose. Right. Now this is going to give you A transpose times A transpose. Okay, so this is the property number 4 in the list of properties of transpose, right? So this, right, this from property number 1, this give me A times times A transpose. So the transpose of AA transpose is equal to itself. So therefore, A times A transpose is a symmetric matrix, right? And using the similar manner, use the property number 4, can calculate that A transpose of that product give you A transpose times A transpose of transpose, give me A transpose times A. Right, so the property I use again is properties number 4. And this is property number 1. Right, so as well as this case is property number 1. So this calculation also shows that A transpose times A is a symmetric matrix. Okay. So basically that's it for me for this lecture. In this lecture, we look at different properties of matrix additions and scalar multiplications, as well as the properties of matrix multiplications, right? And toward the end of the lecture, we look at the properties of transpose of the matrix, right? So that's it for me. Please let me know if you have any questions. Thank you.